Hello, welcome to the sixth and final video in the sequence on C++ models. In this final video, we're going to discuss templates, and then we'll draw some conclusions about C++ models in general and show you where to find some resources. Okay, so templates. Suppose that we have a point class that's templatized on a parameter t. In the last video, we showed you a point class that used double type for coordinates, but we may need a more general type than that. So if we templatize that class point with a template parameter t, where t is the type of the coordinates. So each coordinate could be, for example, an instance of a class that had some information about the coordinate and stuff, or whatever. Could be an int, could be a double, could be a, float. So, so we have a template class point. Now, templates are code generators. The function template generates functions instantiated for each of the types supplied to the template. So if I supply an int and a double, I get two functions, one using an int parameter and one using a double parameter, and the same thing for classes. Very often the template operation is almost a substitution. Sometimes it's a lot more than that, but we'll see that as we go along. So, so they're function generators, and here I've shown a point class, templatized point class, and if I instantiate it for ints, I get a class point of int. And it has some objects that, you can create with that class. If I instantiate it for a double, I get a class point double, and you can instantiate that and get some points where the coordinate in this case are doubles and the coordinates in this case are integers. And I can have both at once, and that what that means is that there's two classes, and these are separate classes. Point int and point double are distinct classes. So for example, if I had a static data member in the templated point class, the int class would have a static. The double would have a static, but the static in the int class shares its value with all instances of that class, but it doesn't share them with the point double. And similarly, the static in point double shares with all the instances of the point double class, but it doesn't share them with point int. Okay, so we have a code generator that application code caused to generate two separate classes, and we can create points with those. All right, so here's an example of a template class. So this is the point class, and now we've parameterized that with type T using templates. Otherwise, it's the same class. Now notice that where I had double here, I substituted T. I had to initialize a list of doubles, substituted with T. Return double types, and here I'm returning T types. Here I had a vector of doubles, now I have a vector of T's. So this is, for this class, is almost totally just a substitution process. For some classes, again, it may be more than that, but a lot of classes, it's just basically a substitution class. And so each of the member types have to be prefaced with this template type named T. So here's the constructor, one of the constructors for the point class. Remember that any function with the same name as the class is a constructor for the class. And here I've said point of T, : point, size of n, and the string name. So n describes the number of coordinates and of type T, and string is just a name. Notice that here I specifically provided the parameter in between angle brackets for this, and I didn't here. What's the difference? Here I'm using point as a type. Here I'm using point as a function name. So you provide this parameterization for types, not for function names. And here I'm using an initialization sequence for name, and I'm reserving some coordinates, the n, room for n coordinates with my constructor. And here's a constructor for initializer list, and it just keeps pushing back the items. So I don't specify the n here, it's just I'm going to have the number of coordinates equal to however many things I have in my parameterized list, where each item in the parameterized list is the value of some coordinate. Value of the data held in some coordinate. And so on, and I didn't, there wasn't enough room. I've elided some of the methods, but basically this is a nice example of a template class and some of the advantages of template classes. Now, I get a lot of flexibility here because I can simply substitute different types for T. But that's not the end of the flexibility story. I can have an ordinary class that takes is a templated class that takes an argument where the argument is an implementation for some of its functions. So for example, I might have a directory navigator that's looking for directories and files, but we don't want to wire into that directory navigator what it does when it finds a directory and what it does when it finds a file. We want that navigator class is really useful. We want to be able to apply it to any application that needs navigation without changing the navigator at all. And we could do that with templates. So we make the navigator templatize on a type name A, where A stands for the application. And A might provide a function do file and do dir that specifies what that application needs for files and directories. And another application would have a similarly designed class that had do file and do dir that did the things that that application wanted. So we get a lot of flexibility by using templates. Okay, so one more part of that story, which we won't elaborate a whole bunch here, but with templates, the generic class or function may operate well for a bunch of different types, but there may be one or two types that our application wants to use in which that generic processing doesn't work. So we'd like to be able to specialize for those cases the code so that will work for those types. And for functions, we simply overload the function with those specific types. And the language guarantees for a function, if I have a template function and I've overloaded that for some specific type, if the application instantiates that parameter with that specific type that was overloaded, then it will choose the overload. But if I don't have a match to the overload, then it just uses the generic. For any type that doesn't match an overload, it just uses the generic type. And that's very useful, very flexible. It extends the range of the operation of these templates. And the same thing with classes. Instead of overloading, now we're specializing, what's called specialization of the template. But again, if we have a generic template that works for a lot of types, but there's one or two types it doesn't work well for, we can provide a class, full class definition that uses the explicit parameter, those explicit types in place of the templates, in place of the template parameter. And the language guarantees that if the template type matches a specialization, it'll compile the specialization. If the type doesn't match any specialization, then it'll compile the generic type. And again, this is just a nice way of extending the range of those template classes. So there's some subtleties associated, especially with the class specializations, that we cover in some detail in the CPP story. But here our intent is just to provide good mental models for the way the language goes about its business. So we'll reserve those details for you to look at when you read through the C++ story. And again, we're going to come to the conclusions in the next slide, and we'll show you how to find that stuff. So C++ provides two great ways of supporting the development of flexible code. Inheritance and polymorphism allows us to add new specialized derived classes that don't break existing code, and templates allow us to provide arguments that specify some type we want to use, and if we want to instantiate it for a new type, we just created a widget type and we instantiate it for widgets. That'll, you know, as long as everything else is syntactically a match, that works fine. So two great ways of writing flexible code. If you look at the C++ story, you'll see nice examples of both of those kinds of building flexibility into code. Okay, so let's draw some conclusions. We're at the end of our C++ models, not the end of the C++ story, but remember, these C++ models were just the first chapter in our C++ story. And so we're going to wind that up here. So if you understand, there's 8 models we've provided. And if you understand those 8 models, especially the C++ object model, if you understand those, you're going to find that the language syntax and semantics are consistent and sensible and fairly easy to understand and use. You know, it isn't you know, hard, complex. It's a big language and an ambitious language, but it isn't nearly as complex as it in some quarters has a reputation of being. It's very sensible and very regular. In some ways, it's more regular than some of the other languages that are touted to be simpler. So some particular parts of the language are discussed in the CPP story, but not here. Require some fairly detailed study: template type deduction, function overload resolution, template metaprogramming. All of these things get into some fairly sophisticated details, and again, we cover a lot of that in the C++ story, so you're invited to go take a look at that, and I'll show you where in just a second. Okay, but you know, generally, template type deduction just works. You know, you don't need to understand these sophisticated details. Every once in a while, it doesn't, and you need to fall back and look at some of those. You know, what happened? Why did that happen? But it's rare. Usually, it works just the way you'd expect it to work. Template metaprogramming traditionally has been quite complex and sophisticated, kind of hard to use. But with each version of the language, C++ 11, then C++ 14, and now especially C++ 17, template metaprogramming has gotten significantly easier to use. There's some very common things we want to use that are almost trivial to do with the parts of C++ 17, and you'll see examples of that in the C++ story. We're not going to talk about them here, but here's where you can find stuff. So the website is you know, jimfoss@github.io, and the C++ story starts with this. This is the first page of the C++ story. Now these stories are linked collections of pages, and each page, you know, if you look at the top menu, you'll see a next and prev buttons, and if you click next, you'll go to the next in the sequence. Also, it responds to keyboard commands. If you hit N on the keyboard, it'll move to the next one. If you hit P on the keyboard, it'll move to the previous one. So this is a linked set of pages, and there's also a lot of code examples for the story. The story is fairly detailed. There's a lot of code examples, and you'll find them in this CPP story repository. And this will take you directly to that repository, and you can download it and build the projects. One word of note, virtually all of this code has to be has to be compiled with the C++17 standard option. By default, Visual Studio, for example, doesn't use the C++. It uses what I think is C++11 as the default standard, but it's simple, one click. You go to the property sheet and you click to get the C++17 option going, and then should all compile. Everything there should compile. From this story, the first chapter are C++ models, and I've abstracted from that chapter these videos. So these videos represent in some detail what's in that first chapter. There's some stuff in the chapter that isn't in the videos, just for space and time. The presentation slides on these models you can find here in the website resources, CppModels.pdf. Pull that down. That's what we've been looking at in these videos, are this set of PDFs. And if you open the home page of the website, you'll see at the top a link to videos, and that will take you to all the videos. You know, there's a table with all these videos in it. You just click on them and start up the videos. So, and here's, you know, here are links. Here I showed you but these aren't clickable links. Here are the clickable links for that. So with that, we're going to stop. It's been a pleasure doing these videos. I hope you've enjoyed them. If you have, feel free to send me comments. I have a Piazza account just to take comments and bug reports and stuff like that for this website. You're welcome to do that. You know, look on Piazza for that. Or, you know, if you have my email, you can send me an email. That works fine too. With that, been a pleasure talking to you, and we will say one last time, we'll say goodbye.